Well, today I'm going to be talking about our final product on vectors, and this is known as the vector product, also known as a cross product. The word vector in the name is about describing what the output is. You see both in the scalar product and in the vector product, the inputs are two vectors. So we have, let me give you a sort of a diagram for this. You can think of the dot product as a function that takes two inputs. The inputs are one vector, and I'm going to call this u, and the second thing is another vector. Let's call that one v. And the output is a scalar, a real number, which, is the dot product of those things. If you wanted to say it, you'd write u dot v. I'm just trying to re-emphasize that that thing is just a number. Now, the vector product, which is written with an X like that, this diagram mostly looks the same. You've got two inputs, a vector u and a vector v. So if you think about it, really in both of these there's 6 numbers going in, right? Well, it depends. If you're in R3, there are three numbers for each of these vectors, so that's 6 total numbers as inputs. And in the case of the scalar product, a single number comes out. But in the case of the vector product, a vector comes out. That's huge. I'd just like to point out that in R2, we already do know a way to multiply pairs of numbers. Pairs with pairs to get a pair. Yeah, so is it possible to multiply pairs of real numbers and get another real number? Well, complex arithmetic does that. You see, it's when you talk about a complex number, usually you write it as a plus bi. But this is really just a question of decorations. What effectively that is a pair of things, right? An a in the real component and a b in the imaginary part. But you could just as easily think of this as the vector with components a and b. In other words, when you're thinking about the thing as a complex number, a plus bi is a spot in the real versus imaginary plane. The real has 1 along the real axis, the imaginary has a marker I along the vertical axis, and that point is a plus bi. But I think in this light, the only difference, frankly, is that we're calling this the x-axis and the y-axis, and a plus bi is thought of as a directed thing, going from the origin out to that position. So you could think of it as a pair, you can think of it as a vector, and you can think of it as a complex number, right? That's just changing your perspective on it, but the real point is that we have a way to multiply those. With complex arithmetic, you just FOIL rule. If I have 2 of them, a plus bi and c plus di. First, actually, I like to call it the Floy rule when I'm doing complex numbers, because the real things are the first times first and the last times last, because you'll get bd, but I squared, bd, I. But I squared is -1. That's the whole point of I. It's the square root of -1. So the first and the last entries give you AC minus BD. The things that end up still having an I in them, let's see, what's that? They'll be from outer times outer, there's AD, and from inner times inner, there's BC. those numbers all times I. Right, so this is effectively a way to say if I've got a vector and another vector, I can just put their components together in a special way. It would be A comma B times by C comma D would equal, what's in the x coordinate? AC minus BD. And what's in the y coordinate? AD plus BC. There is a reasonable way to multiply pairs. So there was a famous mathematician named William Rowan Hamilton. I searched online and found an interesting thing here. This is a image of a stamp from the Republic of Ireland that commemorates this guy. He was Irish. I don't know if you can make out the stuff that's in bluish green there. That's his famous fundamental equation for a thing called the quaternions. So let me talk a little about Hamilton. He was a brilliant mathematician, but for quite a while, like many years, he got fixated on this kind of a question. He knew that with complex arithmetic, we could multiply pairs of numbers. And he wanted to know, is it possible to multiply triples? So, William Rowan Hamilton. Basically, what his question was, is there a 3D analog of complex multiplication? So apparently he got so fixated on this thing that he sort of dropped every other duty he had. He was lucky he could arrange to not teach for extended periods of time. He was a university professor, but he took it upon himself to solve this question. It was it was of burning importance to him. And there's this anecdote about his children got used to him spending every day locked in his study. He'd go upstairs and lock himself in and spend the entire day trying to figure out a way to multiply triples. And it got to be a thing, apparently, with the kids. They would tease him every morning before he went upstairs, or, they're having breakfast together, I presume. And they would be like, well, Papa, have you learned to multiply triples yet? And I imagine they just annoyed the hell out of him, but he persevered, he stuck with this. And when he finally figured out what to do, he got so excited, he went out to a nearby bridge, and it was a stone bridge with apparently with a toolkit. He took a chisel out to this bridge and he carved the equations into this bridge. It was kind of amazing. So here's what his realization was: instead of triples, what you actually had to do was go to 4 dimensions. So the answer was a thing that they now call quaternions. This is a real thing, but basically what you do, instead of having an I, the square root of -1, you have 3 of those. You have 3 distinct square roots of -1, and he called them I, J, and K. So we start off with ABI, but there'll be some multiple of J, and there'll also be some multiple of K. And you can see this is just like, using decorations to create a 4-dimensional vector. A, B, C, D are the components of it. Well, if you multiply 2 things like this, now that'll get pretty intense, and I don't want to get into the full detail of it, but what you need to do is figure out what happens with I's and J's and K's, and then, distributive law and a lot of simplifying. maybe I should do one example of it just to show you that it can work. But what happens with ij's and k's? Well, here's the equations that Hamilton carved into the bridge. I squared and j squared and k squared are all the same, and they equal -1. So these are each one of those ijk things is a square root of -1. And then also, if you multiply two of them, you get the third. So ij is equal to k, but this is the first place where we really see officially in math a case of non-commutativity. If you do ji, that'll be -k. So if you change the order, if they're sort of in alphabetical order, you get k. If they're in the opposite of alphabetical order, you get the negative of k. There's also, let's see, jk will give you I, and kj is -I. I'm sure Hamilton planned it out better than I did with the space, because there's one more set of equations, set of these sort of pairs of products. What would it be? I and k. So let's see, ki is j, and ik is the negative of j. So these relationships and the fact that those variables squared equals -1 allows you to multiply things that look like that are sort of the 4D generalizations of a complex number. I think I'll leave these rules at the bottom of the page, and we'll do a quick example of this, and then we'll push on. I'm just going to make up some numbers for the multipliers, the real part, and then the multipliers of ij and k. So how about like 2 plus I minus j plus 3k. That'll be one such quaternion. And how about 1 minus I plus j plus k. I'm trying to keep it so that I work with small numbers just to make it easy. But you know, the multipliers in front of these could be arbitrary. All right, so well, if you actually, you know what? I'm just going to show you a general technique. This is not something you need to know about, honestly, in your math career, how to rapidly multiply quaternions. But here's how you do it. You make a table. And you put one quaternion. You have to watch out the order. So this was the first one. We'll put it into the rows. 2i minus j, 3k. The other one we'll put into the column headings. 1 minus I plus j plus k. And then we'll fill out this table by multiplying rows times columns. Well, the first one's easy. 2 times 1 is 2. 2 times minus I is minus 2i. Okay, plus 2j plus 2k. That first row is easy. Here's going to get tougher. We need to do I times the column headings. So the first one will be an I. I times I is -1. There's also a minus sign there, so that gives us a 1. I times j, remember that if they were in alphabetical order, you get k. So this is just k right there. And I times k, I guess I'll actually show you the way people actually remember this rule. Take them in the order I to j to k and back to I. If you're following these arrows, if you've got I and j, you'll get k. You'll get the next one, j and k, you'll get I. But if you're going against the arrows, that's when you'll get the negative one. So what I want to do right here is I times k. I to k is going backwards, so we get negative of j there. All right, I'm going to just fill it out quickly for the rest of it. Minus j plus ji, that's -1. That's minus k, excuse me. Plus sign, because those things cancel. J times I is going, yeah, minus k. All right, minus j times plus j, that's 1. minus j times k, that's in order you get I, but there's a minus sign. 3k, there, ki. That's in the right order, so j, but it's minus 3 times j. Kj backwards, so that's minus I, and there's a 3 on it, minus 3I. And lastly, 3 times k squared. 3 times k, that's minus 3. And the things that are like terms that have the same ij or k on them are in predictable locations. So it's not quite as easy as working with polynomials, but you see all the real numbers are right there. So it's going to be 2 plus 1 plus 1 plus minus 3. It ends up just being a 1. The things that have i's in them are in little like 2 back diagonal things here. So there's minus 1 there, and there's minus 4 there, total of minus 5. The j's are in forward slanting diagonals there and there. And let's see, there's 1j there, and there's minus 4j's there. That's a total of minus 3j. And the k's, 3 down 1, oh, these two cancel, 3 and 2, 5k. So if you ever wanted to know how to multiply triples, here's the answer. You can't multiply triples, but you can multiply 4 tuples. And you know, triples are a subset of the 4 tuples. Basically, if you set the imaginary part, sorry, the real part to 0, then you've got a triple. And so people talked about pure imaginary quaternions. All right, so I didn't get a picture of the other character in this saga, but our guy Hamilton ended up having quite a debate, although long distance and over time, with an American mathematician named Josiah Willard Gibbs. And Gibbs, I believe he was at Yale, but in any case, he was the first president of the American Math Society. He was a big shot in America, but at this time, America was the backwoods, right? And so even though he was a professor at Yale, he wasn't considered important on the national stage. But it was a big deal here. And him disagreeing with somebody from continental Europe was a little strange, I guess, but it worked. He eventually succeeded in getting most people to adopt his view of, you know, what's the right way to multiply triples. So Hamilton had his pure imaginary quaternions. Gibbs was a real pragmatic guy. He didn't like this jumping to 4 dimensions, and you know, because what's 4D? There's no fourth dimension. Well, a couple of decades later, Einstein came along and said, no, actually, space and time together make a 4-dimensional thing, and so you know, the proper place to do physics is in 4-dimensional space. So Gibbs's pragmatism quickly got replaced with, you know, a different outlook. But in any case, Gibbs said, look, all that stuff with the quaternions, it's nice, but there's a very simple rule that you can do instead, and it'll just directly take one vector and multiply it times another vector, length 3 vectors. So he looked at a vector A, B, C, crossed with cross gap x, a second vector, say it's D, E, F. And it turns out that the multiplication we're about to do is the same as this quaternionic thing, but, well, it's a good bit less work. Really it is. So what he did was use a thing called a determinant. And determinants are shown by putting absolute value bars around an array of numbers. Okay. And what we're going to put in this array of numbers are I, J, and K. That sounds like Hamilton's things, but J.W. Gibbs didn't think of these guys as Hamilton's square roots of -1 at all. He thought of them as particular vectors. Now I'll tell you what I, j, and k are, because they're really quite important vectors. I is the vector that has a 1 in the x coordinate and 0, 0, or else. J, that has a 1 in the y coordinate and 0's in the other two positions. And K, oops, needs a tag. K has it in the z slot. And so this set of vectors are called the unit vectors because they're length 1. You see that each one of them it's only got one non-zero coordinate, so the sum of the squares is easy to compute. You get 1, right? Yeah, so these are called the unit vectors. And together they sort of give you how you're going to do the coordinates. It gives you a vector in the, remember my right-hand rule thing? I, J, and K are my fingers and thumb. They're the length 1. I guess these look like they're slightly different lengths. In fact, they are, because that's the way fingers work. But if you make them all the same length, here, I'll try to do it with markers. I will be black, J will be red, K will be green. I can't do it. I can barely do it. Here's a system of the unit vectors there. They're all perpendicular to each other. A quick, easy dot product calculation tells you the dot products are all 0. So you get 3 mutually orthogonal vectors of length 1. It forms what's known as a basis. But we'll talk, well, you'll get to talk about that more in Calc 3 and if you take it linear algebra. Let me finish off how you do this computation. You put the entries of the first vector into the next row after the I, J, and K, and the second one into the third row. And then your multiplication, well, you know, it really does come from the arithmetic of Hamilton's stuff, but it's, I don't know, there's a pattern to it that makes it easier to remember. You don't have to go through all the work. Can I kill this? The pattern is this. You want to figure out the stuff that multiplies I, you look everywhere else. All right, so the multiplier on I is going to come from these 4 numbers. And here's the pattern. You add going this way, and then you subtract going that way. So it's I times BF minus CE. Or let's do it this way, BF minus CE times I. I'm going to skip one. I'm not going to do J right now, but there's also something that we'll fill in here in a minute, and that will be times J. Oh, that's not a regular I, that's an I with a hat. Because K is also easy to deal with. So can I just make some changes to this picture? I want to think about getting the K component. Just try to erase all those extra lines I put in. Oh, heck. Let me just redo that part. This was B and C, and this was E and F. So now, when I do K, I circle K, and I look at the other 2 columns and the other 2 rows. That is, I look at these 4 numbers. And just like before, in this direction, we'll be taking a product and counting it as positive, and this way, negative. So it's AE minus BD. So why did I want to skip J? Because there's a slight complication with J in that you have to think about this not as being on a flat. a good way to think of it is imagine the whole thing is taking place on a video game screen. And so if you know one of those games, like if you go off this side, you'll reappear on that side. That's how the things for J have to work, because if you think about it, when I did a similar diagram to what I've done for the other cases, you know what? Being lazy, let me just get it to look right. This row was A, B, and C. This row was D, E, and F. And if I was interested in the stuff that goes with J, it's supposed to be everything except that row and column, right? So it's these things and these things. And you should think of them as also being a square. It just wraps around the side. So this line goes over there and then comes back in on this side. And in fact, I can draw around the perimeter of this square for you. Go off there, come on this side, go down here, come off, go back on this side, go back to the beginning. Get the idea? So the product that is positive is still the one that trumps this way. Will be plus sign going that way, but it goes around the corner and hits there. So it's CD that's positive, and it's AF that's negative. That product goes off that way. Well, as long as you can think about it, a lot of people just do AF, CD, minus CD, and then remember that there's an extra minus sign. Whatever you do to make this work is fine. But I prefer to think about it as wrapping around. So what did I just say it would be? CD minus AF. Now, I've written this as multiplying the i's and the j's and the k's, right? These involving these unit vectors. But remember what I is. It's a vector that's got a 1 in the first slot and zeros elsewhere. So if I times that scalar times, let's write it all out. Sorry. What is it? BF minus CE times I is the same thing as BF times minus CE times 1, 0, 0, that vector. And then we have CD minus AF, and that's multiplied by the vector J, which is 0, 1, 0. And finally, we're adding, what's our last guy? AE minus BD, and that's times the vector 0, 0, 1. So I'm going to have to kill the machine that we use to produce these values, but as a vector, this is now, it's got that number in the first position. So it's BF minus CE. It's got CD minus AF in the y coordinate. And it's got AE minus BD in the z coordinate. So Gibbs' approach to it was just like, here's what you do. This is the process, and it gets you a vector. There's some really cool stuff, though, about this particular vector. So let me illustrate the geometry of it. If you have a vector U and another vector V, think of these as in 3D space. So I'm actually sort of thinking that's almost pointing on the x-axis, and that's pointing more along the y-axis. Their cross product is perpendicular to both of them. So, and it turns out it's a right-hand rule kind of thing. You point your fingers down U, you curl them towards V, and your thumb will point in the direction of the new vector. So your new vector will be perpendicular to both. This is U cross V. That's a cool fact. They don't look like it, but that's perpendicular and that's perpendicular. It's just because of the projection, right? All right, and then what else? Well, the size of this guy is related to the sizes of the inputs. If you make one of the inputs twice as big, you get a twice as big cross product. And it turns out the size of it is the area of the parallelogram you get when you try to add these two guys. That's just kind of amazing stuff. And there's more. This cross product calculation is exactly the right thing to do when you're interested in computing torques. So it has a mechanics kind of meaning to it as well. If you're thinking about torque the right way, torque is actually a vector quantity. Let me erase and I'll give you an extended example about torque. All right, so I'm assuming everybody's familiar with this kind of an object, a combination wrench. This is it's kind of a nicely designed thing. It's got not just a hexagon in here, but a 12-pointed star, which means that if you have a bolt like this, you can get it on there in a lot of different positions. But the main idea of torque is that you're going to put a wrench onto a bolt and then you're going to rotate to try to tighten it or loosen it, right? And that's why it's a vector quantity. There's a saying amongst mechanics, righty-tighty, lefty-loosey, which is a bad saying, to be honest. You should say clockwise is tightening and anti-clockwise is loosening, but I guess it doesn't sound as good. So turning to the right means over the top of the arc, it's heading to the right. If you actually do mechanics work, I should point out, it's wise to give yourself this kind of a wrench. This is called a torque wrench, and it has a dial back here, which you can adjust. And you know, I'm not sure if I wanted to show you, but it can be read pretty accurately. And you set a torque value on this, and then when you torque your bolt to that amount, it gives a click. There's an audible, and you can feel it as well, this little bump that says, okay, you just reached the right torque. Why do you want one of these? Because a lot of things in modern cars are not over-designed. The fasteners and the things that they go into are designed to work at exactly the right torque, and if you just try to estimate that and you go too much, you end up shearing the head off the bolt, and if you don't do enough, the thing gets loose over time and falls out while you're driving, and that could, you know, depending on what that thing is holding, it could be kind of a big deal. So getting correct torque values is something that home mechanics tend to forget about, and it can be quite dangerous to not get those set right properly. So that said, why is this a vector quantity? If I put my wrench on here, and I guess I'm going to try to draw the wrench now too. I'll just draw the open-ended part of it. This now is invisible because it's hidden by the wrench. The wrench comes out here some distance. That's a terrible looking wrench, but I think you get the idea. If I push on the end of this wrench, I'm applying a force, right? That's a vector. And the distance out from here that I apply the force, that matters. For instance, one of the things that you do in practice when you've got a bolt that's stuck or that you can't get enough pressure on it to really tighten it the way you want it, is you get a piece of a thing that they call a cheater in mechanics shops. And if you go into any car shop, there'll be a cheater sitting in a corner somewhere. It's basically a pipe that's big enough to fit over the end of this thing. And now you've got a wrench that's 4 feet long instead of 1 foot long. So you can torque yourself mad with that. So if the length of the place where you apply the force matters, and that's going to be another vector from the center of the nut out to the location where we apply the force. And so the torque is a vector, and it's gotten by doing the cross product. You have this applied force, and you cross it with, let's call this vector r, because it's sort of radial, F cross r. So that's going to be, I was trying to draw it into the board with this F vector. Did it look like, maybe I should draw it like I normally draw the y-axis. Excuse me. So F crossed with R, if I'm going in this direction, would I be tightening? F crossed with R, actually, F crossed R, yeah. That's a vector that goes this way. So T would be sticking up. I fear I may have done the wrong thing. Maybe I'm supposed to have R going the other direction. But in any case, if I applied the F on this side instead of on this side, in the direction that would be loosening the nut, then I'd be putting a minus sign on F, and so I'd get the negative of this T. Right? The right-hand rule with an F that went this way crossed with our torque, with our radial vector, that ends up as a T that goes the other direction. That's what makes it a vector. And people often call these results of a cross product calculation polar vectors, because they always point along the pole of the rotation. Sometimes also axial vectors. So torque is this physical quantity, and it is encapsulated with the cross product. The cross product tells you how to calculate the torque vector. The direction of the torque vector, apparently, I'm pretty sure I've messed something up, and I'll have to stop and sort this out. But I always thought that the direction of the torque vector told you sort of which way the bolt is trying to move. That is, if we're tightening, the bolt is trying to go into the material. If we're loosening, it's trying to move out. And this would seem to be the reverse of that. But perhaps I'm just misremembering. Also, I apparently was using a see-through wrench through that. Glass wrenches are not a good idea. All right, let's do one little piece further of theory, and then like I said, I'll check up on the direction of T, and we'll sort that out. The other piece of theory is to figure out exactly what is the magnitude of our torque. So in general, if you have a vector u crossed with a vector v, you know the cross product is going to go that way. It'll be perpendicular to both of them. U cross v's magnitude, because it is a vector, and so we've sort of figured out the direction of it based on it's got to be perpendicular to those guys. The magnitude of u cross v, I said it before, it's the area of the parallelogram. But the area of the parallelogram has a nice interpretation. It's the length of the product of the lengths of the two vectors times the sine of the angle between them. Remember how in the dot product, the angle between them, you ended up with the cosine? It's just exactly like the expression in the dot product, except it's a sine instead of a cosine. Why is it that gets you the area of the parallelogram? Let me rotate these guys into place so that they're drawn in a plane, just the regular XY plane. I don't know where they are in 3 space, but I can just always arrange for them to look like this. U will be a vector in the x direction. I'm just going to put the plane's coordinates on there in such a way that this happens. The angle theta will be there at the origin, and V will be whatever V is, right? So the parallelogram looks like this, right? And do you know how a formula for the area of a parallelogram? Well, it turns out it's just the area of the base times the altitude of the thing. How tall is it? Well, okay, the base is just the length of our first vector. This was u, wasn't it? Yeah. So the base here is the length of u. How tall is this? What is this dimension from the line determined by u and the tip of the vector v? Well, do you see that this hypotenuse of a, you see there's a right triangle in here again. The hypotenuse of this right triangle is v. Here's the right triangle. Theta is the side, this angle, and the side we're after is this question mark thing here, the one where the height of the parallelogram. And that is just, well, it's the side of opposite theta, so that's the sine of the angle, except scaled by this, because the hypotenuse isn't 1, it's the length of v. So this height I've been talking about is length of v times the sine of theta. There's the base, this part's the height. The product of the two together gives you the area of that parallelogram. So, let's see. When do you get the largest possible value of the cross product? Well, if you really have, a wrench on something, don't you always try to push it so that the direction of the wrench is, the applied force is exactly 90 degrees to the direction of the wrench? I mean, imagine having this thing and trying to push it that way towards the nut or bolt or whatever it is. Even if it's at some angle, you're effectively greatly reducing your moment arm for the torque. So you don't want to do that. You don't want to be pulling on the wrench. You want to push it 90 degrees to the axis of the wrench, to the R vector. And that's really clear in this formulation for the size of u cross v. When is u cross v going to be maximum? You can't change the size of u, and well, maybe you could, but imagining the vectors u and v are relatively fixed, but their sizes are fixed, but you can maybe adjust the angle. When does sine theta get as big as possible? Yeah, that really does make sense if you're in the torque calculation, right? U is the length of the wrench. I mean, the size of U is the length of the wrench. The size of V is, well, I'm only so strong. I can maybe apply 80 pounds of force. That's about it. So I can't make that bigger unless I just trade me for some other mechanic who's stronger. But I can adjust this. I can make sure that I'm putting the torque, I'm creating the maximum torque by applying that force perpendicular to the axis of the wrench. Yeah, so when is sine theta biggest? Of course, when theta is pi over 2 or 90 degrees. So maximum is when that's a right angle. And if you've got u cross v in the other order, so it's v cross u, it'll go the opposite direction. Right, so I was just reviewing that last clip to figure out where I went wrong in the torque calculation, and two things struck my attention. One is that I was talking about the click sound that this makes when you reach the appropriate torque, and you're probably hearing what you're hearing now. Well, trust me, the lowest setting on this thing is about 20 foot-pounds, and there's no way I can apply 20 foot-pounds of torque through a lever arm that's about half an inch around. So that sound is this thing is a ratchet as well. It spins relatively freely in one direction and resists it in the other. I did some experimenting, and again, at the lowest setting, I can't find any way to actually reproduce the click sound. But if you have this on a bolt in your car or on some machine, you have no trouble getting enough resistance to make the click happen, and it's quite obvious when it does. The other thing, which was wrong, is when I did the torque calculation, I did it, the torque is the force applied crossed with the radial vector. And this is not right. And The rule I mentioned about, the direction of the torque vector, that polar vector is supposed to be in the direction the bolt would tend to move, or the nut would tend to move, either one. That happens because the threads on fasteners are almost always what are called right-handed threads. So if you do the torque calculation the other way, then that check follows. So if you do torque is the radial vector crossed with the force, that'll work out. So let's suppose we're looking down on top of a bolt. So we've got a hexagonal bolt there, and you put a wrench on it. I'm having a hard time drawing good wrenches today. I don't know why that is. All right, so our radial vector out to the point where force would be applied would be something like that. And the force, using the righty-tighty rule, I would need to go this way, right, to spin it farther down into the thing. If I wanted to get a vector out of the board, loosening, I would go this way. Let's try that. If I apply a force like this, do I get the right thing? Well, one problem is that the force vector and the radial vector are kind of lined up the wrong way. I would like to parallel transport this vector. Move this force vector till it's tail to tail with the radial vector. And now we're going to do R cross F. So take your fingers of your right hand, point them in the direction of R, and then curl them towards F, and your thumb is giving you an outward pointing torque vector. So this would be loosening, the bolt would be tending to come out of the machine part or whatever it's in. Yeah, and so that was it, just the order was messed up. My memory isn't what it used to be, I guess. I thought I'd show you a couple of other options for how to carry out the cross product calculation. Yeah, so again, let's make up a couple of vectors. How about U is 1, 2, 5, and B is 3, -1, 7. I have no idea how that's going to work out, but let's do a cross product calculation. So if I'm going to do U cross V, I make a determinant with I, J, and K in the top row, and it's U first, so 1, 2, 5 in the middle row, and then 3, -1, 7 in the bottom row. So the approach that many people like, I'm kind of a fan, but I find that in the end I don't need to do this. But at least conceptually what you do is make a copy of your first row right here. I, 1, and 3. And some people even make a copy of their second, I think I just said first row, that's a column, isn't it? I made a copy of my first column over here to the right. Some people will also make a copy of their second column over here, but that's not necessary. Oh, so why is this useful to do? Well, let me use some colors to try to indicate what's going on. When I go about using I, or finding the I coordinate, the things that involve I, it's I times this product, where it's plus going down and minus going down. When I go to do J, I get the same exact pattern. So J would look like J times this pattern. Again, positive on the way down, negative on the, well, down to the right is positive, down to the left is negative. And have I got a third color? Well, I have to do black is the third color. Finally, K would be the same pattern, but with those other guys. So if you do it that, wow, I've made such a horrible mess of the drawing. I'm not sure if we can work it out. But I find that I can often just fill in the entries by going, okay, the I guy is 14 minus -5. Product of 2 and 7 minus the product of 5 and minus 1. Wait a minute, that's 14 minus negative 5, so 14 plus 5, we get 19 in the I slot. In the J slot, that's the stuff in red, it'll be 15 minus 7. That is 8. And the K, that'll be negative 1 minus 6, negative 7. Do you see that that's fairly quick? You see the same little pattern, down with plus signs, back with minus signs, in each of the I, J, and K positions. So it allows you to write out the vector quickly. I like to write it in the vector with angle braces and commas. It's really the same thing to write it in the IJK form, though. You could say 19 times I plus 8 times J minus 7 times K. These are equivalent. One thing I want you to know, though, is don't mix them up. That looks weird. That is, if you write it in IJK form, the angle braces don't need to be there, and in fact shouldn't be there. So putting something like angle braces with 19I, 8J, and minus 7K, this produces sadness on my part. I'm trying to make an unhappy face. Yeah, just don't do that. It's one or the other. Either use the IJK notation or use the angle braces notation. One last theory thing I want to go through, and then we'll have a final application to electromagnetism, which is another place where the cross-product calculation shows up very naturally. The first thing is theory. What about these unit vectors? What if I take the cross products of them? I cross J, for instance, or J cross K, or there's a lot of different possibilities for. I guess there's 6 different ways that you could write a cross product involving 2 of those things. But let's start with just looking at I cross J. Well, remember this is the vector 1, 0, 0, and this is the vector 0, 1, 0. So I could just do the cross product calculation the way we learned to do it, right? IJ and K in the top row, the first vector in the second row, the second vector in the third row. And then you're taking the determinant of that. All right, so it's I times 0 minus 0. Okay, so that's 0 times I. J times 0 minus, I can't do that. Okay, so you know what? I'm going to do copy the first column idea again. All right, so this is going to be I, that one is true, it's 0 times I. For J, it's 0 minus 0. Okay, so it's also 0 times J. And for K, it's 1 minus 0. So what do we see? That I cross J equals K. Now, other than the vector hats on this, that's Hamilton's quaternion equation, that the I and J's product would give you K, except the product has a cross in front of it instead of just a times. Yeah, so in fact this computation with unit vectors actually tells you that the algebra we're getting by doing the cross product in terms of I, J's, and K's is exactly the same thing as Hamilton's quaternions with pure imaginary vectors, or pure imaginary quaternions. Do you want to see that J cross I is equal to the negative K? How would that look? It would just, I said J cross I, so that would be O1O cross 1O. So let's fix these two. I can get away with the eraser here, can I? 1, 0, 0 there. Here it's 0, 1, 0. But this is the important place to see it. My My extra column is wrong though now. It should be I01. What do we get out of that computation? It's 1 times 0 minus 0 times 0, so total of 0 times I. For j, it's 0 times 1 minus 0 times 0, still 0. And for k, it's 0 times 0 minus 1 times 1. Oh, we get minus 1k. J cross I is minus k. You can do the computations I've just done also geometrically. So let's take a quick look at that. In that standard way of drawing 3D space I showed you before, with x off to the right and z vertical and y going into the board. These unit vectors, actually I think I better make y a little bit longer than that. These unit vectors are vectors that point right along the axes. If we shift them so their tails are right at the origin, they're vectors pointing out along the axis. So for instance, here's I. This one would be j, and this one would be k. And remember, the geometric rule is you use the right-hand rule to figure out what direction a thing goes, which you can do. And the size of the thing is the area of the parallelogram, the addition parallelogram. So suppose I did I cross k. I put my fingers along I curl them towards k, my thumb points out of the board. So I know it's in the direction opposite to j, and its magnitude is what? Well, how big is the I cross k parallelogram? It's a 1 by 1 square. So it's the magnitude of this result is 1, but it points in the negative j direction, so it is indeed negative j. Let me give you another quick example of that. What do you get if you do j cross k? J's into the board, so point your fingers into the board, curl them towards the z-axis, that means coming up, and your thumb ends up pointing out along the x-axis in the direction of vector I. And so its length, again, it's the magnitude of it is the size of the parallelogram, which is again a 1 by 1 square. So j cross k is I. Excuse me. I actually tend to remember this by the same diagram people use for quaternions, except it has cross products in it. It's if you have I cross j, whoops, j, okay, I cross j, you'll get, that is just the worst j. I gotta start over. I cross j gives you k, k cross I gives you j, ij is k, ki is j, what else is it? jk is I, you know, any circularly, following one of these arrows, that'll get you the thing. And if you go against the arrows, it gives you a minus sign. So using that little diagram, you can quickly go I cross j equals k, j cross I, forget these all need vector hats. The j cross I is against the arrow, so it's negative k. Perhaps it's not worth me doing that all out, but you get the idea. So yeah, those are how the unit vectors work. We did it both by looking at a determinant and also just by the geometry of cross products, and that's pretty cool. So the last thing, the application I wanted to mention to you is how magnetic fields act on moving charged particles. A a charged particle moving in a magnetic, man, this is out of steam, isn't it? That's better. A charged particle moving in a magnetic field experiences a force. This is kind of cool. This force that a charged particle experiences in a magnetic field is what makes motors and generators run. It's also what makes the magnetic field of the Earth sustain and build. There's a dynamo effect inside the Earth in the core. Interaction with solar wind, that's I believe the theory of that. Actually, I'm not sure if I got that right. But in any case, this is true. If you have a charged particle that's moving in a magnetic field, it experiences a force. And the way this force works, it's perpendicular to the direction of motion. So it's also perpendicular to the magnetic field. The magnetic field is almost universally called B. So B with a vector hat on it is a magnetic field. And it's also perpendicular to the direction of motion. That's the velocity of the object, so we normally call that V. So one of the ways that you see this applied is in particle physics. They have a device called a cloud chamber, and it's a chamber that's full of very humid, cool air. So cool that the slightest disturbance will make water come out of solution, basically, condense into little droplets. So when a particle passes through a cloud chamber, that's enough of a disturbance to cause this condensation. So you see these little vapor trails behind charged particles that are moving through a cloud chamber. It's pretty cool. And if you put a magnetic field across the cloud chamber, as a particle enters it, it experiences this force that's perpendicular both to the direction it's moving and to the applied field. So if I have a cloud chamber seen from above, it might look like something like this, and the exit line for a particle accelerator might be here. So high-speed particles are entering the cloud chamber here. The magnetic field is actually going into the board. So let's draw it like that, but really it's perpendicular to the board. Sometimes people draw a vector like that's that way, that it's supposed to be going into the board like this, by putting an X on it. It's supposed to make you think about the feathers that you see on an arrow in archery. And if you draw it the other way, that's a circle with a dot in the middle is like the point of the arrowhead coming towards you. So you know it's coming towards you this way, going away that way. Let's suppose it's going away. So we've got a magnetic field B into the board. My velocity vector, of course, is this way. What's a force, what's a direction that's perpendicular to both of those? This one's into the board, this one's that way. The only possibility is that way, right? So the force exerted on this thing goes this way. Well, it depends actually on the charge of the particle. If the charged particle is, I believe it's negative ones that will curl the way I'm expecting. But if I have a charged particle that's moving this way and it's a force applied is kind of against, or not against, but perpendicular to the direction of motion, do you see that that's going to cause it to curve? And in fact, what happens is it slows down, it curves around and goes into like a spiral, a death spin. And you know, it's really fascinating to see these images of cloud chambers. You should Google that and see what you can tell from that. For instance, if the particle was the same charge as this guy, but much heavier, the force applied will only cause it to deviate a little bit, right? So slight curvature, the direction of curvature tells you what the charge is. How much curvature there is tells you how heavy the thing is. You can get a lot of information out of the motion of this object in a magnetic field. I'm sorry, inattentive, I gotta fix that. I just made it worse. Anyway, yeah, that's the force applied, well, that's the heuristics of the force applied to a charged particle. Let's get the actual formula. The force that the particle experiences is a cross product, and it depends on two things. One is how much charge you have times the velocity vector. So if you're thinking about these as just electrons or protons, the charge would always be 1. But if it was something like the nucleus of a helium atom, then the charge would be 2. And generally speaking, it's an integer multiple of 1. Although, you know, yeah, well, quarks supposedly have charges of 1/3 and 2/3 and stuff like that, but you never see quarks naked. They always run together, so that the net charge on things is always integers. All right, so that's one part of it, and the other part is the magnetic field. So Q times the velocity vector crossed with B. That gets you the force applied. Sometimes people take the Q out of this calculation and just write it out front. It's Q times B cross B. Whatever floats your boat, they're the same thing. So yeah, this whole equation I've written right here is part of Maxwell's equations for electromagnetism. There's a whole bunch of those, and if you take Calc 3, you do get to the point where you can literally understand Maxwell's equations. They're very weird and complicated if you see them expressed without these vector operations. But when you see them expressed with the vector operations, they become really sweet. They're really quite easy to follow. Okay, so that's it for today.